Warm welcome from my side. Today's topic for the webinar is balancing STV cybersecurity and performance requirements using the HSM. So, let me first start with a short introduction about myself. My name is Rohan Pandit. I'm part of the product management team at ETAS. I'm located in Stuttgart, in Germany. I've been part of ETAS's product management team focusing on the embedded security domain since 2018. So I have approximately 6 years of domain knowledge with embedded security here. Okay, with that, let's jump into the agenda for today. So we'll first start with a short webinar goal topic. And then we jump into the core topic, which is the impact of STVs on cybersecurity, how the evolution of cybersecurity requirements has evolved along with the introduction of STVs. What are some of the new security challenges which can be resolved using the HSM or the hardware security module? A look at long-term security, specifically as defined by UNECE R155 requirements, and then we will open up for a Q&A. All right, so let's start first with the goals for today's webinar. So our first goal is to understand how cybersecurity is impacted by the introduction of software-defined vehicle. Our second goal is to understand how the evolution of hardware and software are used to address these new requirements. And finally, the third goal for today's webinar would be how the HSM solutions can be used to address some of these key challenges. Let's first start now with the impact of STV on cybersecurity. So the STV will be communicating via different channels, as we see in this picture here. It's not just about communicating with the traditional internal ECU level communication, but we are talking about multiple layers of communications here, both internal and external to the vehicle. As we see in the picture, there are multiple layers of communication with the vehicle connected to several layers across the ecosystem. So here we are talking about vehicle to grid, vehicle to infrastructure, to smart devices, on the next level also to the backend systems and other vehicles, and also to vehicle SoC as well. This means that there will be a continuous flow of data across the various channels throughout the life cycle of the vehicle. The introduction of all these changes introduces also several new attack vectors, which means that this will have a significant impact on how cybersecurity systems are in place and how it has to be adapted going into the future for STV. So in order to be prepared, we need to also have a solution in place which is able to address the potential attack vectors, the new attack vectors that are arising because of the introduction of STVs. Okay. Then let's have a look at cybersecurity from a UNECE perspective. For vehicles of today, UNECE cybersecurity maturity level 3 is sufficient. However, going into the future, we will have to have a more advanced or higher level of cybersecurity maturity level as defined by UNECE. Here we are talking about 3 dimensions. So the first dimension is the life cycle, the second one being software supply chain, and the third one being ecosystem. So for a new end-to-end security, there needs to be protection ensured from design level to production to the end of life. This means this is the life cycle dimension which has to be covered. Then we have the software supply chain dimension, where we have to ensure protection from customers to manufacturers to both existing and new software suppliers, which also includes open source software projects. For the third dimension, the ecosystem dimension, we have to also ensure that in-vehicle components which are connected to mobile devices, vehicle clouds, and infrastructure vendors and operators. So the communication channels that we saw on the previous slide are also protected as well. So we see that there is a significant update in terms of cybersecurity requirements also from UNECE point of view in order to have a secure system for the software-defined vehicle. Okay. Then we move to the next section, which is the evolution of cybersecurity requirements. So if we look at this picture here, we see that the automotive world has evolved over time in terms of EE architecture. We see a clear transition from more function-specific ECUs in today's world in order to handle the complex vehicle functions. And we see a transition towards more domain-specific ECUs, which are needed for the future. Currently, we are in the domain or cross-domain centralized architecture phase and gradually moving upwards. Now, this architectural shift will lead into consolidation of several functionalities and consequently reduced hardware, but more software-based solutions. So going into the future, this is expected to become a more and more domain-independent architecture with a vehicle-centralized approach, and eventually increasing the number of functions which are available in the cloud. So long story short, with the evolution of EE architecture, we have a lot more complexity which has to be handled from a security perspective, and we need a new and improved solution which can address these challenges. So let's have a look then how we can have this storyline here. So step one. So first, the evolution of EE architecture is leading to a chain of events in the automotive domain. So first step is the evolution of EE architecture, which we saw in the previous slide, which is leading to a much higher software complexity due to the shift of several functionalities from hardware to software. There are several new communication channels which result in a need for an increased network communication. There is requirement for having modular firmware upgrades to the components without affecting the overall system. There is also a need for a next level security hardening system in place to address the new wider attack surface that we see in the new EE architecture. Also, we see more and more ECUs have several suppliers contributing towards the ECU development based on the expertise. And we have to ensure that all the different suppliers can contribute towards ECU development without impacting the other components in the system. So all of these changes then have resulted in a major update also on the hardware layer. So all the new automotive microcontrollers include increased memory sizes to support more and more new features and additional resources which can be stored on the microcontroller memory. There is a significantly improved performance. This is attained by two steps. One is the new security IP, which is the dedicated hardware accelerators with multiple channels. The Second aspect is the enhanced crypto accelerators, both for asymmetric and symmetric crypto algorithms, which also increase the number of crypto algorithms supported in comparison to the predecessor. Of course, another major update is the support for virtualization, which also includes granular level of access right controls as well. And all of these hardware changes then consequently also demand for an evolution in the security firmware on the HSM as well. So the new HSM firmware would be leveraging the capabilities of the new hardware in order to address the challenges that we see emerging out of the architecture changes. So we've talked about all of these changes and the challenges that we see due to the introduction of SDV and the architecture evolution. And here we can have a look in the next section about some of the new security challenges which can be resolved using HSM. So here I've taken two challenges, focusing on one on the performance while the other on the cybersecurity requirements. The first challenge we look at is the SecOC bandwidth challenge. So the key challenge for the HSM is to attain a good balance between security and performance, especially when we are talking about secure onboard communication, because security is focusing on ensuring freedom from interference by isolating the host and HSM from each other. Here, the the HSM acts as a root of trust and ensures overall ECU security. But at the same time, performance is an essential requirement for broadband data transmission between the host and the HSM cores, especially in an SDV environment where we see a lot more communication channels and hence a much broader data flow as well. In the current Avita-based architecture microcontrollers, we see that there is a bottleneck, which is the bridge between the host and the HSM. As we see in this picture, for a SecOC message, it has to pass through all the different layers on the host side stack, then reach the bridge, then go through the HSM firmware, then use the AES hardware engine to get the message out, and then the output has to return through the same path. From the root itself, we can see that this is quite a long path and this acts as a bottleneck to the SecOC challenge that we have. So how do we try to address this challenge? So the new microcontroller architecture added a new SecOC accelerator IP. So this is what we also saw in one of the previous slides. So the next generation of targets offer these security IP to address the SecOC bandwidth challenge. So this IP is essentially a hardware accelerator that offers symmetric crypto capabilities with parallel FIFOs. So in order to ensure security, the keys are still being calculated and loaded from the classic HSM IP, but the host itself is able to place a SecOC operation directly to the security IP here. So this, if we look at the root itself, the SecOC message can be easily retrieved in a much shorter route, which leads to much improved performance using the SecOC accelerator IPs. So in addition to this, because of this new SecOC accelerator, it also allows for a much clearer safe CMAC path as well. So safe CMAC in very short would be the requirement for ASIL-D to ensure that no false MAC message shall be verified as valid, and a freedom from interference is ensured between HSM and host. So this is the solution for the SecOC bandwidth challenge. Now let's look at another new challenge that we have with the introduction of SDVs. So let's take here scenario 1, where the HSM is trusted, but the host could be compromised. In this case, there are two options. The request from the application software could be used to perform a trusted chain of operations with an untrusted host. However, this is not the ideal scenario that we would like to have. The second option is to perform a chain of operations with intermediate values which are not leaving the HSM, so still within the secured HSM world. But again, this is also leading to much limited operations. Let's look at scenario 2. Here we have two application softwares, software A and B. And here in our example, we say that, okay, application A is a trusted application. So we can, of course, accept requests from this application software. However, application software B could be compromised. So in this case, we have to ensure that the requests from the compromised software are not accepted, but at the same time ensure that any requests coming in from software A are still being accepted, although there is a compromised software application B. And how do we address this challenge? So this is realized using the support for virtualization feature, which has been added on the new microcontroller devices. So virtualization support using the HSM can be used for several use cases. So the first use case is for updating the firmware. So virtualization would offer the flexibility to update each virtual machine independently using the OTA without affecting the overall system downtime. Another key use case would be in a multi-tier 1 collaboration model, where virtualization enables easy integration of software from multiple vendors while protecting the IP and ensuring freedom from interference as well. The second aspect is with respect to access management. So an access management system can be set up using the HSM so as to ensure isolation of critical resources such as keys and certificates for each and every virtual machine. So this also enables an effective implementation of the safety critical use cases by limitation of the context itself. So for example, if host application 1 or virtual machine 1 is a safety critical virtual machine, then the access to the resources for virtual machine 1 can be defined and configured as only accessible to this specific virtual machine and cannot be granted to other virtual machines in the system. So this provides a much more granular level of access rights control. Another big improvement would be with respect to performance as well. So the overall startup time for the ECU can also be improved here by efficient allocation of computing power towards the relevant VMs, which can be configured in the end by the user. So in general, with the introduction of virtualization, we are able to not only resolve the issues of multi-user environments, but also gain several other advantages such as access management, performance, safety use cases, and flexible updates. All right, then let's move to the next section. So this is about long-term security, and this is based on the UNECE requirements R155. So here we are talking about crypto agility. In very simple terms, crypto agility means that in order to be on the safe side, you must be faster with adapting to new security challenges than the attackers are in creating new successful attacks. So let's use Michel Mosca's theorem here. So according to his theorem, the time to react for exchanging crypto algorithms depends on three factors. So the first factor is the security shelf life, which is, for example, X years. Here we are talking about how long do the key resources such as data and keys need to be secure. The second factor is migration time, which is, for example, Y years. How long does it take for it to migrate to a safer solution? And the third factor is collapse time, or Z years. When does a large scale attack take place? So if we look at the timeline here, if X plus Y, so security shelf life plus migration time, is higher or greater than the collapse time, then we have a problem. So we need to ensure that the migration time is, or the security shelf life plus migration time is always lesser than the time for a collapse or for a time for an attack to take place. So here we need to have dynamic and fast adaptations to new security challenges which might occur in the future, and we have to be proactive enough to make our systems robust and secure before a large scale attack takes place. So this is an introduction to crypto agility. Let's deep dive a little bit into the details. So the migration time can be divided into several phases. It starts firstly with the pure existence of a new security mechanism. This is where we currently look for crypto algorithms which are robust against attacks by post quantum computers, for example. So, researchers are working continuously to identify algorithms which can cope with this new challenge. Of course, then after this step, they have to go through several selection rounds, for example, in the NIST standardization group, until the selected crypto algorithms are standardized. Of course, what is still missing is the standardization of which PQC algorithms to use and for what kind of specific automotive use cases. So, on the protocol level, the existence phase is something which is ongoing. The next phase is to make new security mechanisms available for all peers, including the ECU. The idea is to have the public key interface in full automotive quality, all the domains, including host and the HSM as well, by having a fail-safe update process in place. The rollout then continues with the next step, which is the activation by a switchover process. And finally, there is a system in place to manage the monitoring process and handle further improvements. This is mainly covered by regulatory and standards defined by UNECE, ISO 21434, or the Cybersecurity Management System. So these are the different phases of the migrations. Let's take an example now of PQC challenge. So PQC is now a big challenge that the industry anticipates in the new future, where we have post quantum cryptography, which can be used to create large-scale attacks. So we foresee that PQC will pose a severe security threat to current crypto algorithms. A common example would be lowering the security level for AES by a factor of 2, and is also making it very easy to break existing ECC and RSA algorithms as well. So citing these threats, several OEMs have already started including PQC requirements in their security specifications. NIST is already in the process of selecting PQC algorithms and have already selected a couple of algorithms which are standardized by NIST already. So these are Dilithium and Sphinx Plus. So in general, all ECUs need to establish a secure design to be prepared against post-quantum computer attacks. And consequently, the HSM also has to do the same on the HSM firmware side as well. So this is an example of an existing PQC challenge. So how do we make sure that the availability of the new crypto algorithms can be made before a large-scale attack takes place? So the new security mechanisms can be made available to the vehicles by using secured over-the-air updates for both host and the HSM using the FOTA or SOTA functionality. Also, to ensure that there is a fallback option in case of a failure, there are several options which we can use. So there's an option to swap between the active and inactive flashbang. Of course, this is provided that it is supported by the hardware itself. The second option would be to have a signature-based verification in case of a CMAC failure. The third option is, of course, mirroring or having a backup copy of the mandatory software parts. In addition, a patent pending technology to provide dynamic updates without changing the core binary is also being evaluated here. So in principle, we have several ways of making the new updates available onto the vehicle. The next step, of course, is activation, which we don't have to go into the details. So we then move on to the management phase. So here I've just given an example of ETA's Cycle HSM, which is already certified by TÜV according to the ISO 21434. And this includes certification for the product as well as the process. And for the process, we are following the ETA Cybersecurity Management System, which is based on the SAP process here. So this covers the different phases of existence, availability, activation, and management in case of a long-term security plan. Okay, so now we are entering into the final section where I would like to summarize then what are the requirements from an HSM perspective in order to address the challenges of SDV. Okay, so in an SDV world, we have identified some key aspects, especially relevant from an HSM perspective. So the first aspect is multi-application support. As all the new hardware devices offer support for virtualization, the HSM firmware also needs to manage these requests efficiently to ensure optimal performance. The second aspect is with respect to secure boot and onboard communication performance, which is provided by accelerating using the hardware accelerators available on these devices. The third aspect is the configuration, which eases the overall integration process and reduces overall product development time. In the end, this is resulting in cost savings for the customers. And finally, but not the least, is the requirement to have a future-ready solution, which is compliant with the UNECE requirements. So something which is PQC ready and also offers support for crypto agility. So this is a high-level overview of HSM requirements for an SDV world. So for this, we have a solution available from ETAS, which is the Script CycleHSM 3.x. This is a new generation of HSM firmware provided by ETAS, and this offers much more in terms of crypto features, hardware support, and configuration options. So if we look at the first aspect here, so in terms of the feature set, so in addition to all the existing basic features that are already available on the current HSM software, we also have added new features such as the dedicated host hardware accelerator support that we already covered in the presentation today. We have support for virtual environments as well. We have features which are dedicated for production specific use cases. This is quite an underrated feature because this results in optimizing the production process and eventually leading to cost savings for the customers. Also, we have a PQC ready solution. This is achieved by using a combination of CycleLib, which is the software library for ETAS, and using the crypto accelerators to achieve best performance. The second aspect here is the plug and play solution. So all major OEM use cases are already supported and proven in field as well with the current generation of HSM, and all these new features will be added in addition to the existing features that are already available on the HSM firmware. Of course, we also have a solution that is compatible with both AUTOSAR and non-AUTOSAR environments, because we see that there are several customers who are opting for different options here, either to be in the AUTOSAR world or having their more proprietary software solution, which is a non-AUTOSAR compliant environment. The third aspect is about easy configuration and usability. So we offer flexibility here to the customer to use a pre-configured solution, which is created by ETAS based on the requirement specifications that are required by the OEMs. So we have already analyzed and come up with a configuration which is meeting to specific OEM requirements. Of course, the user also has the flexibility to configure according to their own requirements using an easy configuration tool. Also, one important thing is that we also want to offer a smooth transition path for the existing CycleHSM users so that they can easily transition into CycleHSM 3.x world. And the final aspect is about the range of devices supported. I have only listed down the three families here, so Infineon TC4X, the Renesas U2X family, and the Stellar family from STMicro. These are only three of the target families that I've listed, but of course we have support and a roadmap for several other silicon vendors as well. So to summarize here, we have in Script CycleHSM 3.x a new generation of HSM, which is developed to address the complex new software-defined vehicle requirements. This is not just a minor increment from what we have on the 2.x, but a major update to address the needs of an SDV world.